Hello, in this lecture we will first introduce RMS-prop, which, similarly to momentum, is an improved variant of gradient descent. Then we will introduce ADAM, which combines momentum and RMS-prop and is one of the most used optimization algorithms to train neural networks. In gradient descent, depending on the choice of the learning rate, we could either have slow convergence or zigzag behavior that may even lead to divergent behavior. One way to reduce both of these issues is to adding momentum to gradient descent. We will now introduce RMS-prop, which also improves gradient descent by alleviating both problems. To gain some intuition before formally introducing RMS-prop, let's consider the function in blue. You can see that in the red circle the function has a plateau. This plateau is a problem for gradient descent because even though the gradient is non-zero, it is very small, thus making the convergence slow. If you think about how small the gradient of a sigmoid function is when far from the origin, you can understand that this is a common problem in neural network training. However, if you look at this problem more carefully, you can realize that the sign of the gradient still points in the correct directions. And what creates really problems is its magnitude. RMS-prop is built on this intuition. In RMS-prop, we normalize the gradient by its moving average. This allows us to still have relatively fast convergence even when the gradient is small. Note that V, the square moving average of the gradient, weights the current gradient with the previous one. This has also the effect of reducing the zigzag behavior and speeding up convergence. In fact, if both current and previous gradients in a given direction were large, then V will be large in that direction, which means that the gradient is divided by something big. Similarly, if in a given direction all the gradients were small, then the current gradient in that direction will be divided by something small, thus obtaining something large. Epsilon is just needed to avoid division by 0, and is typically always taken to be 10 at minus 8. Adam take momentum and RMS-prop and combine them together. In particularly, in the first line, we have that M is an estimation of the gradient with momentum, while V is the second moment of the gradient as in RMS-prop. The update of the gradient is as you may expect. The new candidate optimal x is obtained by subtracting the learning rate times m divided by the square root of v plus epsilon to the current gradient, to the current x. In practice, values of beta 1 and beta 2 and epsilon are more or less always kept fixed to the recommended values shown in the table in here, while the learning rate, in general, needs tuning. A practical implementation of ADAM generally uses bias corrections on both M and V. For instance, if we are at iteration k, then we divide M by 1 minus beta 1 to the power of k, and V by 1 minus beta 2 to the power of k. This helps to get more accurate gradient estimations, especially for small k. To understand this, let's assume k equal 1. It is easy to see that with the bias correction, we obtain that m1 is equal to the gradient of f in x0. In fact, note that m at iteration k minus 1 would be 0 because we are at the first iteration. And with the bias correction, you get 1 minus beta 1 divided by 1 minus beta 1 times the gradient of f, which of course is equal to the gradient of f. Instead, without bias correction, we have that m1 would be 1 minus beta 1 times the gradient of f. As beta 1 is generally large, as you saw in the table, this would mean a large underestimation of the gradient that will then be propagated over time through the moving average. We have now introduced ADAM, which combines momentum, RMS-prop and bias corrections. This is one of the most used algorithms to train neural networks.